Unit 4 of this grade 11 physics course is about electricity and magnetism. Now you might already know that there's a connection between electricity and magnetism. We're going to learn a bit more about it in this unit. It's mainly going to focus on splitting them up though, so we're going to start with electricity, then we're going to learn about magnetism, and then we're going to combine them to talk about electromagnetism. So first, in order to learn about electricity, we need to understand the concept of electric current. Now, what exactly is electricity? So we can define electricity in a number of different ways. We can define it off of units like amperes or units like voltage. But one way of deciding, I guess, what electricity is to consider it as the movement of electrical charge through a conductor. And how much charge we have that moves through that conductor, we would have more electricity. So electric current is the movement of charge. The SI unit is amperes, but the symbol for electric current is a capital I. In the 1700s, Benjamin Franklin, who was a well-known American scientist, he flew a kite during a light storm to investigate the nature of electricity. He decided that when describing electricity, an excess electricity, or the charge that makes up the electricity, is positive, and a deficit of electricity is negative. So in other words, the charge moves from the positive terminal to the negative terminal of the source of electric potential. So basically, when Benjamin Franklin ended up kind of defining electricity, he defined the current flow of electricity as going from the positive terminal to the negative terminal, and that's the conventional direction that we use. However, after we understood electricity a bit more, we determined that electricity can also be thought of as the move of electrons. And that move of electrons actually occurs in the opposite direction, which we'll get to soon. But I'll finish this slide here. It says, note that the lightning did not strike the kite directly. That would have immediately destroyed the kite and seriously injured or killed Benjamin Franklin. So this is the flow of electricity as defined by conventional current. This is the kind that the current flow that is used in technology and in industry. So it's important to understand the conventional current flow. It is when we have electricity flowing from a positive terminal through a circuit back to the negative terminal. So this was the convention of electricity that we used to describe electric flow for over 150 years. When the electron was discovered, there was a chance to understand electricity a bit more, and it was determined that what's actually happening when that charge is flowing, it's actually the flow of electrons going from one atom to another, to another, to another, to another, inside of a conductor. And that flow of electrons actually occurs in the opposite direction. It goes from the negative terminal to the positive terminal. That's the direction of electron flow. Our direction of electric current, though, has been defined as the opposite. So that is kind of a situation we have in science and technology now. It's interesting to note that we still use both, even though the electron flow is really the more correct one. What we'll learn about later in this unit is a number of rules to define direction of electromotive force and direction of magnetic fields, and those are all based off of the conventional current flow, not the electron flow. So electron flow is when those negatively charged electrons move from the negative terminal to the positive terminal. And it's in the opposite direction. You can see here with the arrows, it goes from negative through the circuit back to positive. So we'll need to know both of those, electron flow and conventional current flow. Mainly when we do our problems, though, we'll be using conventional current flow. It might help to realize that a positive charge flowing east along a wire is electrically equivalent in every way to a negative charge flowing west. So this is another interesting sort of situation. If we have, because it's possible to have positive and negative charges moving. So there might be positive ions that are flowing. And if those positive ions are flowing, in this case here, let's say these positive ions are flowing to the right. Well, in that case, our current would be directed right. If we have negative ions or electrons, which is most commonly what moves around in electricity, flowing to the left, that current flow, the conventional current flow, would still be in the same direction to the right. So this is an interesting aspect because we're dealing with charges that can either attract or repel. So the direction they move and their polarity, their positive or negativeness, affects how we define the current. So further on with electric current, we have two more types to talk about here. There is direct current, and direct current is it's easiest to understand with a graph here. It's defined as a certain voltage level or current level that is unchanging. So it's direct. It's literally, it stays the same the entire time. This is the kind of current you would see from a battery or a lot of portable electric devices. So the current does not change at all. So direct current flows in one direction only, and you see this with batteries or solar cells. And then there's other sort of things like piezoelectric meters and other types of things that you would see, but for our purposes, just write down batteries and solar cells. Another type of electric current that we have is alternating current. This is when we have a sinusoidal output of our electric current, and the reason why this type of current is useful is that it's more efficient to distribute electrical energy over longer distances, and you have the option to power more complex devices. So this is the type of electricity you see plugged out of a wall outlet, and it is current that moves back and forth. It alternates direction. Another thing to note as well, when we're above the x-axis here, we're flowing in one direction. When we're below the x-axis, we're flowing in the opposite direction. So it constantly flows back and forth. At one point, it'll flow this way through the circuit. At another point, it'll flow this way through the circuit. How do we measure electric current? Well, we do that with a device called an ammeter. An ammeter, it measures the amount of electric current in a circuit. It is connected in series, which means that we kind of connect it along the series of the circuit. So in this case, our electricity would flow from our positive terminal to our load, to our ammeter, and then back to our negative terminal. Then we are able to measure our amperage or our current in that series connection. So you can copy this information down for an ammeter. The symbol for it is a circle with an A. And we'll talk a little bit about circuit symbols when we get into our circuit analysis later in this unit. in this unit. The other thing to mention is you may not have a dedicated ammeter, but you might be using what's called a multimeter. A multimeter can measure a number of different electrical properties depending on how it's connected and what its setting is. So here, a student's trying to measure the current through this circuit, specifically the current that's going through this light bulb here. That's the symbol for a lamp or a light bulb. If they connect their ammeter like this, an ammeter really has no electrical resistance or very little electrical resistance, which means that electric current flows through it quite easily. And if this was the case, our current typically will flow through the path of least resistance first. And if it sees that this lamp has a certain amount of resistance, but this path here has very little resistance, we'll actually travel more through the ammeter than we will through this lamp here. So we won't be able to measure the current of this lamp. We actually have a short circuit a type of design here, and this this ammeter will not measure anything. We won't be measuring the amperage through that light bulb. Here's an interesting did you know. The nerve cells in your body communicate with each other by creating small electric currents. If a larger current is transmitted through your body, it can overload your nervous system. By touching a wire with a current flowing through it, you can affect the current in your body. Muscles contract and you may not be able to let go of the wire. The electric current will also cause burns because some of the electrical energy will be transformed into thermal energy. So if you've ever been electrocuted, I hope you haven't, but you might notice that you feel stuck, almost like you're magnetically attracted to the thing that's electrocuting you. It's because the electricity is actually contracting your muscles against what your nervous system would try to tell you to do. This is sometimes what you can do is you can use if you're being electrocuted on one hand, you can use the other hand to push your body away from that because you're basically going to be stuck holding on to that. Last point here. A current of 0.016 amps or 16 milliamps is sometimes referred to as the let go threshold, because if the current is above this value, the person cannot let go of the object giving the electric shock. So that current level, 16 milliamps, is the kind of like the threshold where you're able to counteract the electrical caused contraction of your muscles. Anything greater than that means you'll be stuck. And that's the point that we're going to end this lecture on.